Okay, with 12.4, we're going to deal with vector multiplication. That's very different from the dot product. The dot product would always multiply two vectors to a scalar, to just a regular old number, positive or negative. Today, our multiplication will yield a vector. If we have two non-zero vectors that are not parallel, they'll determine a plane. They could make a flat surface just like a piece of paper or a piece of cardboard. Imagine two arrows are in it. There is a unit vector perpendicular to this plane by the right-hand rule. We can call that vector n. The cross product, very important definition here, is that vector A cross vector B would be the length of A, the length of B multiplied together, times the sine of the angle between them, multiplied to this unit vector that corresponds to our right-hand rule. Take a look at the picture down below. I have A and B. If I put my right hand on vector A and curled it towards vector B, my thumb would point upwards. This would be vector A cross vector B. This would be a vector that's perpendicular to both of those vectors A and B. If A and B were actually on one flat sheet of paper, the piece of paper on your notes, A cross B would be coming out towards you. The length of vector A cross B, of course, is going to be, you can see, multiplied to this unit vector, the length of A times the length of B times the sine of the angle in between. By way of comparison, if we were to change the order, B cross A, well, that's where we'd have to start with our right hand on B and curl our fingers towards A. We'd have to put our hand upside down to do that. We talked about that in class. This would be vector B cross A. You can see that we'd be going in an opposite direction of A cross B, and we would have vector B cross A perpendicular to both. The cross product, like I was just saying, is going to be perpendicular to both of the original vectors. For the first time, we're seeing multiplication where order matters. Our cross product is not commutative. If you change the order, you'll get the opposite vector. We just saw that up above. Two non-zero vectors are parallel if and only if their cross products is the zero vector. Think about it this way. If you're parallel, the angle between your two vectors will be 0 or 180 degrees. Come up here to this definition that we're seeing right here. And if you had 0 degrees or if you had 180 degrees, the sine of that would be 0. So your cross product would yield 0. Here's an application that we can get into. It's kind of a nice one. If you take a look at the cross product of two vectors, we're going to make a claim and say it's the area of a parallelogram. Let's say that I give you vector A cross vector B in this problem, but before we even get into that, let's just review a few things. What's the area of a parallelogram? The area of a parallelogram, plain and simply, is the length of the base times the height. Now you look down here and you can see that your base would be the length of vector A. Your height, though, must go from the highest point, drop down a perpendicular, you could call that h, and I hope you can see a right triangle here. I've drawn that off to the side. Here's this right triangle with the height. The hypotenuse would be the length of vector B. We can certainly use trig. Sine is the opposite over the hypotenuse, so we're going to say sine of theta is h over the length of vector B. Multiply by the length of vector B, and you'll have your height right here. Well, going back to what I highlighted, the area is going to be the length of the base times the height. That's vector A in length multiplied to vector B in length times the sine of theta. That should look relatively familiar. I think what kids might get a little bit confused with at first is they'll say, well, what about vector n in that formula at the top of the page? Remember, vector n has a length of 1. So if you looked at the length of the cross product, remember a vector is an arrow. We can find the length of that arrow, the magnitude of it. the magnitude of the left side would equal the magnitude on the right side. That's where we're going right here. And what you're going to see, hopefully quickly, is that the length of the unit vector gets thrown in as well. That's a length of 1. So what we're going to know is that the area of a parallelogram formed by two vectors is plain and simply the length of the cross product vector. This length is always going to be positive, because we're going to use the length of that arrow. So that's what we have for an immediate application. By the way, if you wanted to envision a triangle that could be formed, imagine we took half of that. You could just take half of the cross product and find the area of a triangle. Some properties of the cross product. We've listed a few here. A cross B is not the same thing as B cross A. It would be only when you take the negative of that cross product on the right side. If you have a constant multiplied out in front, R vector A cross S vector B, it's as if you could just pull both constants out in front and multiply them. If you have A cross B plus C, you could distribute that cross product. Again, on the left, order matters. You want A cross coming first. It would be A cross B plus A cross C. By way of comparison, look at this distribution on this other side. Cross C is always going to maintain that order. It'd be A cross C plus B cross C. And finally, like we were saying, if you have a negative out in front, it would be equivalent to having a negative on the other vector or a negative out in front of both. Well, one thing that we have yet to actually do is talk about how we can find a determinant and how to find this cross product. The determinant is the way to find the cross product of two vectors. Let's say you've got vector A with components of A1, A2, and A3. We're going to list those, of course, in a determinant with ijk up on top. You've got your second vector with B1, B2, B3. We're going to just list that in our third row here. And hopefully you remember in Algebra 2, you dealt with finding the determinant of a matrix like this. And we're actually going to review how to do this right now. Let's see if we could find the cross product of two vectors. So if I gave you A cross B, this would be the determinant with up on top I'll have I, J, and K. And then I'm going to list across, here's 2, 1, 1, -4, 3, and 1. Well, the way we work out a determinant is we recopy the first two rows, the first two columns, excuse me. Remember, columns are vertical. So I'm going to recopy I to -4 and J 1 and 3. And then we're going to do, this is known as the basket weaving method. We're going to take some diagonals here. We'll have I times 1 times 1. You can see, and I've wrote a plus up on top. So that's 1 times 1 times I plus, now we'll go to our next diagonal right here. 1 times -4 times a j, vector j. And then we'll go with our k component here. We'll say plus 2 times 3 times vector k. Well, that's all well and good, but now we're going to switch it up a little bit. We're going to say, well, now I want to go with some minuses. And we're going to put 3 minuses down below and draw some new diagonals. So I'll put a minus. And I'll take -4 times 1 times vector k. And I'll say my next diagonal here would be minus a 3 times 1 times vector I. And finally, we'll take our last diagonal here with this minus down below. We'll say minus 1 times 2 times vector j. And at this point, we just clean it all up. This becomes 1i minus 4j plus 6k. Well, minus a negative 4 times 1 is going to be a plus 4k. This would be a minus 3i, and then we'll say a minus 2j. Tell you what, we'll just combine all our like terms. A 1i and a minus 3i become a minus 2i. Let's take a look at our j's. We have a negative 4j and a negative 2j. That would become a negative 6j. And for our k's, 6k plus 4k would be a 10k. That, guys, is what vector A cross vector B is. And we've got that worked out nicely. By the way, right now I could also tell you we could work this out, but you don't even need to. Vector B cross A would just be the opposite of this. It'd be 2i plus 6j minus 10k. So I want you to try one of these right now. Okay, for our next problem, let's just say that we have a vector perpendicular to the plane is determined by these 3 points. Find a unit vector perpendicular to that plane. So imagine that we've got a plane, a flat surface, and we've got points P, Q, and R, and we'd like to find a vector that's perpendicular and a unit vector at that. Whenever you're looking for a perpendicular vector, the cross product is the way to do it. And dare I say, you want to go back to head minus tail. To find PQ, let's do end minus beginning, and we'll have Q being the ending. We'll say 2 minus a 1, that's your I components. Here's 1 minus negative 1. And finally, we'll have negative 1 minus 0. That's going to yield 1, comma 2, comma negative 1. In a similar way, we can say, well, my goodness, let's see if we could find perhaps PR. Now, I'm going to just pick these out. You could have done other vectors as well. But I'm saying have a starting point of P. So if we looked at PR, again, let's do end minus beginning. We'd have negative 1 minus 1, 1 minus negative 1, and 2 minus 0. Well, PR would be negative 2, 2, and a 2. Well, at this point, you know what we'd really like to do? We'd like to cross these two vectors to find a vector perpendicular to the plane. So real quickly, if we were to say, let's take PQ cross PR, well, that's going to be the determinant. We'll say here's I, here's J, and here's K. Well, let's take a look at PQ. We'd have 1, 2, negative 1. Over here, we'd have negative 2, 2, and 2. What do? Well, we recopy our first 2 columns, just like so. And then we'll use the basket weaving method, plus, plus, plus up on top. So working down this way, we'd have 2 times 2 times I. That would be 4I. And then I'll say plus, well, j times negative 1 times negative 2, that would be a 2j. Could just do all that arithmetic at once. Multiply through with your k's. 2 times 1 times k would be a 2k. From here, let's go upwards. We'll say a negative times a negative 2 is a 2. 2 times 2 is 4. This would be a 4k. Then a negative times a 2 is negative 2. Times negative 1 would be another 2, so that's a 2i. And then finally, coming up with our last one, a negative 2 times a 1 times a j would be a negative 2j. And combining everything up, you'd get 6i. Combining your j's, they completely cancel out, and you'd have a 6k. This, guys, is not a unit vector, though.